So this is a course undertaken in the Department of Material Engineering, and to me speaking, I'm Prof. One. That's my name is Stephen Onoma. I'm in the Department of Material Engineering, and I'm offering metallurgical engineering. So phase transformation is a course that is taken in second year, second semester. Yes, for material. That's for those under the Department of Material Engineering. And when you talk about this is an exciting topic and very interesting. When you understand this, well, with the production of iron and steel, you understand everything. And even not that. So this is the part one edition. That's the part one section of phase transformation. So check the description of this video to get the part two, part three. So the links are under the description of this video for you to get going. So why do we need to study phase? So with phase transformation, it comes in two parts. You study the phase diagrams. After studying the phase diagram, after this the phase diagram, then you go to phase transformation. So we have the phase diagram and phase transformation. So now, why do we need to learn this course? Now, we need to learn this course as a material engineer or metallurgical engineer to develop the understanding of why materials and microstructure undergo changes, and also provide understanding on how the diffusion enable changes in chemical distribution and microstructure of materials, and also formulate and discuss the variety of phase transformation, and discuss the effect of temperature and the driving force of nature of the transformation and its impact on the resulting microstructure. So the whole idea of this course is to understand how materials and microstructures change. So if you understand this course very well, you understand why we have martensite, ferrite, austenite, bainite, and pearlite, and how we can engineering this and get these materials. So one may ask, why do you study phase transformation? Note this, as I told you, the course involved two things: the phase diagrams and phase transformation. Now, why do we need to study phase transformation? First one that we talk about is the development of what? A set of desirable mechanical property of materials often results from a phase transformation. Yes. So if you have a material and you want to give it ductility and you want it to be ductile and also strong, that's how will you do that? That means that you can use phase transformation. You can make sure that you can use quarrying, which is the inside being ductile and the outside being what? Um, that is hard. Like having a martensen, this martensite at the body, that's the martensite at the surface, and the inside having it to be bainite or pearlite. So this is how we engineer this to have this phase transformation. So with this, it's really helped a lot when you understand this course. So now, the time and the temperature dependence of some phase transformations conveniently represent a modified phase diagram. Yes. So with certain time and temperature, you know when this phase happen and when this time happens. So it depends. So we have a diagram that you study. Yes. And this shows the desirable mechanical properties of material can be obtained as a result of phase transformation using heat treatment. Yes. And it's also important to know how to use this phase diagram in order to design a heat treatment procedure of some alloys that will show the desirable room temperature mechanical properties. Tensile strength of iron carbide alloy of eutectoid. When we talk about eutectoid, it's a composition whereby one solid gives two solids. So a solid giving you two solids under cooling. Yes, under cooling. So under cooling, when you are cooling one solid, when you finish cooling, you get two solids. So, and the composition which can be varied between 700 megapascal and 2000 megapascal, depending on the heat treatment employed. So this is why we need to study phase transformation. So this is the introduction of the course. Now, so let's look at the phase diagram of water. As I told you that we have the phase diagrams and the phase transformation. So now this is the phase diagram of water, and with this, the number of phases here is we have the liquid phase, the solid phase, and the vapor phase. So with the phase diagram of water, it has only three phases, which is the solid, liquid, and vapor phase. So we have the pressure against the temperature. So as you can see, there's a triple point where liquid, solid, and gas coexist. The critical point, it means that it cannot go above the critical point, and the boiling point of water, which is 100 degrees Celsius. So this is a phase diagram of a water. This one component phase diagram because it only involves what that is water, one composition. But the phases involved are three, which is the solid phase, the liquid phase, and the vapor phase. So we are going to look at the classification of phase diagrams. Now, when we talk about classification of phase diagrams, we have first one being the diffusion dependent transformation, which is a simple transformation. With that one, there's no change in the number of composition of the phase present. Solidification of pure metals, allotropic transformation, and ray crystallization and grain growth. So with this, it depends, like diffusion depends. It depends on diffusion, right? And we need to know these characteristics. And we have the second one, which is the diffusion dependent transformation. That is the second one. Some alteration. This is the simple and this is the complex one. So some alteration in the phase composition, often alteration in the number of phases, and final microstructure ordinarily consists of two phases, detectoid and other three phases reactions, right? Yes. So this is, and the third one that we need to know is the diffusionless transformation. That's the metastable phase produce and metastatic transformation. That's metastatic transformation of some steel alloys. Now we're going to look at the polymorph and allotropy. That's polymorphism of allotropy. Now, you know that metals exist in more than one crystal form, and changes of this form is called allotropy transformation. So when a metal can exist in one or more forms, we can have some allotropy, like which is carbon, granite. You have the diamond. It can change it, right, and the rest. And also we have some in the metal minerals, right? Yes. So now we're going to look at the allotrope of iron. Now I'm going to make sure bring this one down for you. So when you take iron, now iron we have three, which is the ferrite, the austenite, and the delta ion. Now when you hear alpha, the alpha represents the ferrite ion, and the gamma represents the austenite, and this is the delta ion. So we have some changes, right? So let's see, between the temperature of negative 273 degrees to 912 degrees, then we have BCC ferrite. So BCC ferrite is between this temperature. Now, and between 912 degrees and 1394 degrees, we have the austenite forming. So it means that the BCC then changes to what? FCC. Then within this temperature, that is 1394 degrees and 1539 degrees, we get the delta ion being formed. So the ion is changing from BCC, then go to FCC, then BCC back. Then the melting temperature of ion is this. So it's the melting temperature of ion is 1539 degrees Celsius. So from there we get the liquid ion. So you should know the transformation of ion. Yes, basically when learning phase transformation, they make basically based on the ion carbon phase transformation. So normally it deals with the ion carbon transformation, right? Yes, that is in changes in period transformation. That is from ferrite, which is BCC, to austenite, which is FCC, then delta ion. So you need to know these temperature ranges. It really helps because it will help you when you are doing phase transformation. And also note the melting temperature of iron, which is 1539 centigrade. So now note that ion exists in BC. That's both BCT and what? Both BCC and also FCC form, depending on the temperature. Right? Yeah. So now we're going to talk about the phase diagram. This is introduction to the course, the phase diagram of pure iron. So this is actually the phase diagram of pure iron. As you can see, we have the vapor. So actually we have the temperature against the pressure. We have the liquid. We have the delta ion, which is BCC. We have the austenite, which is FCC. And we have the ferrite, which is BCC. So we have the temperature range. Now, we have something called the cooling curve. Now, when you combine these cooling curves together, you get a phase diagram. So now, how do you produce the cooling curve when phase diagram is given to you of a pure metal? So now, with this, that's when you look at this side, from this line, that's the cooling curve they produce here. So now, I'm going to explain how to get the cooling curve. Now, so for you to get a cooling curve, first, you must draw this, that is temperature against time. So with the cooling curve is temperature against time. Then what you must do is that they will give you a line. You see where this, the line is passing in. They can give you a line which can also come in like this. The whole idea of cooling curve is you are cooling. When you are cooling, what happens? You want to know what changes, what transformation happens when cooling on the phase diagram. So here we are going to look for this side. So now when you are cooling from here, let's assume you are cooling. Now you see this side is liquid phase. So as you can see, the liquid phase, this is the temperature, so it's you are cooling it down to the liquid phase. Now when you get to this side, so it's the moment you are cooling from here, when you hit a line, that is a transformation, you need to indicate the temperature. So now here, the temperature here is, when you trace it, this is what? 1538 degrees. So that is why they indicated this. So you have indicated this. Now, when you look at this, so cooling from liquid to this, we hit this line, which is a temperature of what? 1538 degrees Celsius. So this is why we've indicated the temperature. Now you can see that it was done in a period of time. It has a time period. So this takes some period. So you take a period like this. Then when you hit here, now you see it will take a period of time. Then you cool it down. So we are cooling it down again, and it will hit at which temperature? This temperature, which is 1394. So 1394 will be the next temperature. So when it was cooled, then it changes, then transformed to this, which is the delta ion at a temperature of 1394. So producing the cooling curve, you need to indicate the temperature before you start drawing. So you first indicate where it hits. So we have 1 temperature here, 2 temperature here, we have 3 temperature here. So you indicate the first temperature with this, the second temperature with this, and the third temperature with this. Then you try to have the cooling curve. Cooling curve means you are cooling it, solidifying it. So from the liquid phase, then it's hit at this temperature, which is the melting point of ion, 1538 degrees Celsius. Then it was cooled within this time limit. So it was cooled. Then because the cooling, it depends, so it has some limit of time. Then it comes down, we are cooling it. It hits at this temperature, which is 1394 degrees. So this is 1394 degrees. Then it's sustained for a limit of time. Then it is cooled again here, which is a temperature of what? 9112 degrees Celsius. This is it. Now, when you do that, we have some transformation happening. So you need to indicate the transformation. You can see that this is the liquid phase. So at above 1538 degrees, we have the liquid phase. Then it changes and hits here. So between 1538 degrees to 1394 degrees, which ion is formed? The delta ion. So you indicate that the delta ion was the origin of that. Then between 1394 and 912, we have what? The austenite what? Forming. You have the austenite what? Forming. Because in a range. Then when it's quenched, you are cooling it, then it gets to what? It goes down to form the what? The ferrite, which is the alpha ion. So this is how to produce the cooling curve. So first you need to indicate the temperature that it hits, then you try sustaining it and then cooling it. So it's very simple. It's very simple. Most of the times it comes like that. So you need to learn how to produce more so you can get more. As time moves on, you get more diagrams and how to produce a cooling curve, right? Yes. So you need to know all this thing. Now, from principal materials, you know that we have some crystal structures. So with this crystal, we have the FCC, BCT, the HCP, the BCT. That's the basic. Is it body-centered tetragona? Yeah, body-centered tetragona. So these are it. And also we have the atomic packing factor. That's the higher the atomic packing factor, the easier the material can be formed. So we have the BCC. First we have SC, but SC normally we don't deal with SC. Yes, that is the atomic packing factor of 0.52. We have BCC 0.68, FCC having 0.74, and ACP having 0.74. So now we have some books that you need to read, which will guide you for this course. The book, first one is the William Callister. This book is a very good book for phase transformation. You can download this book from PDF drive for free. So you go to PDF drive, you can download all this. We have the Donald R. Askerman. That one is a very nice book. The science and engineering. We have the solution manual, both the solution manual and also the book itself. So you can get a copy of that. So now we have some definition. Now I'm coming to the definition. So when you come to phase transformation, we have certain definitions and there are basic concepts that you need to understand. So when you talk about homogeneous system in phase transformation, it's a system in which every property of the material is constant irrespective of the coordinate of the system. And we have phase. So phase is a portion of a system that has a uniform physical and chemical characteristics. So a portion with uniform and physical chemical characteristics. When we talk about a single phase is known as what? Homogeneous system. A system with two or more phases is a mixture, which is a heterogeneous system. So these are things you need to know. Another definition, what is a solvent and a solute? You know that a solute dissolves in a solvent, and a solvent is the host or the major component in the solution. Yes, and the solute is the minor component of the solution. And a phase of a thermodynamic system and the state of matter have uniform physical properties. Now, a system is some portion of the universe that is in which to study. Surrounding is the adjacent part of the universe outside the system. So everything outside the system is called a surrounding. A closed system exchange only mechanical, that's exchange mechanical and thermal energy, no mass exchange. But with the open system, it exchange with energy and mass. You should know that. So we have another one, which is the degree of freedom. So the degree of freedom is the number of variables to define a system. Please note that. And intensity property. So with this, the intensity property here is we have the P, which represent the pressure, the temperature, the pH, and the material variables. So we'll be going to the Gibbs rule, and with this Gibbs rule, we are going to apply the degree of freedom, the intensity property, and I'll try to make you understand the main idea behind the intensity property. Right? So we have the intensity property, which is V and M, and pressure, partial pressure. The eutectic transformation is one in which, now I talk about it. So we have eutectoid and eutectic. And when we talk about eutectic, a liquid changes to what? Solid. So when a liquid is transformed into two solids after cooling. And when we talk about eutectoid, when a solid cools and transforms into two solids. That is here. So, but beginning with solid instead of a liquid, it's called eutectoid reaction or eutectoid transformation. You know that. And spinodal decomposition describes a process in which a single phase is cooled and separated into different compositions of that same phase. So you should know that. We have liquid crystals, a state of matter which has properties between those of conventional liquids and those of liquid crystals. And diffusionless transformation is a phase chain that occurs without a long-range diffusion of atoms, but rather by some form of cooperative and homogeneous movement of many atoms as a result in the change of what? Crystal structure. So we are going to look at component phase. Now, solubility limit of a component is a phase in a phase is the maximum amount of the compound that can dissolve in it. So we can have this supersaturated when you go to mixtures, supersaturated and those words. So example is alcohol has unlimited solubility because it dissolves in water completely, but with sugar it has limited solubility. Yes, you should know that. So but you can depending on the temperature, you can increase the solubility of a solid in a solvent, because when you put sugar in water and it gets to the saturated limit or the saturated, then you can increase the temperature. The more you increase the temperature, the solution can therefore accumulate more solids. So the solubility limit is due to, it can change due to what? Temperature increase. So you can, due to temperature difference, but when you increase the temperature you can accumulate more sugar, because when you increase the temperature it becomes syrup, so it takes in more sugar, right? Yes. Now component is the element of, or a compound which are present in the alloy. So let's take some a phase. Now then we have a lot of different definition for phase. It's an homogeneous chemical which has a chemical composition and blah blah blah. So here the physical and the chemical distinct material region that forms. Now let's see something here. You see this? We have the lighter phase and the darker phase. Here we have the component of this aluminum and copper. So please can you comment in section? That's comment for me. Which one represent the aluminum and which one represent the copper? Is it the lighter one represent aluminum or the darker one? Yes. So the answer is that none of them, because the lighter one contains a little amount of copper and a little amount of aluminum, and also the darker one also contains a little amount of copper and a little amount of aluminum. So let's say something. A material may undergo various phase changes during the process. A phase change may include melting, vaporization, sublimation, aluminum copper alloy transformation, recrystallization, or the chemical formation of a compound. Yeah. So we want to talk about the Gibbs rule, as I talked about. So the Gibbs rule describes the thermodynamic state of the material. It also states the degree of freedom available to describe a particular system with various phases and substances. So this is the formula for finding the degree of freedom. So the degree of freedom shows you whether the portion you are looking for is constraint, not constraint, or fixed. So you understand that if the degree of freedom is 0, it means that it's at the triple point. And if the degree of freedom is 1, it means that it's on a curve. And if the degree of freedom is at a specific phase, then it has 2, right? So now let's try to explain the concept that we have, or the data, or the alphabets. So F represents the degree of freedom, the number of variables to define a system. P is the number of phases, and C is the maximum number of components, and the V is the intensity property, which mostly is 2 when you see pressure against temperature or pH against pH. But if it's only maybe composition against pressure, it means that the intensity property is 1. So be careful, not always is 2. It depends on the intensity property. If it's pressure against temperature, then it's 2 because we have pressure and temperature. But if it's pressure against composition, it's only pressure. So the intensity property becomes 1. So now let's read something. The Gibbs rule works best constructing the phase diagram, and those are usually 2-dimensional with pressure along one side and temperature. So now that means that the degree of the V becomes 2, which is the intensity property. At degree, let me look at this. At degree 2, when the degree of freedom is 2, there is no constraint. The system can change either pressure or temperature and be stable without phase transition. If you have 1 degree of freedom, then you either have a constraint, or yes, either what it means that pressure is equal to Kp, K is equal to, or is equal to K, or T is equal to Kt or K, or mixture. So with this, it's then either have constraints. So the degree, it is constraint, right? Yeah. And if it's the degree of freedom is 0, then it is fixed, or better yet, constraint. So when the degree of freedom is 0, it's at the triple point. Note that. And if it's 1, it's on the curve, and if it's 2, it's at a specific phase. So let's look at the merit of phase 2. Now, it's applicable to both physical and chemical equilibria. It requires no information regarding molecular structure, since it's applicable to macroscopic system. You can see it's convenient method of classifying the equilibrium state in terms of phase and what component and degree of freedom. It helps us to predict behaviors of system and a set of variables, and it indicates that different systems with the same degree have similar properties. So yeah, and it helps us to decide whether a system is, so this condition, various system substances will exist together in equilibrium. Some of the substances present will be interconverted. Some of the substances present will be eliminated. We have some limitation to the phase. It can be only applied to system in equilibrium. So if the system is in equilibrium, it cannot be applied to that. And applies to a single equilibrium system.